All right, guys, we are going to start learning about decomposition now. Decomposition are exactly the opposite of synthesis. So we are breaking something down. So we take a relatively complex molecule and we break it down into either simpler molecules or sometimes even down to the elements, okay? So some chemical reactions are essentially the opposite of synthesis reactions. These are classified as decomposition, okay? Decomposition reaction is one in which a single compound is broken down or breaks down into two or more elements or new, simpler compounds. In generic terms, decomposition reactions can be represented as XY breaking down to X and Y. Okay, so here are a few examples. If I take sodium nitride, it will break down into sodium and nitrogen gas. Okay, remember, nitrogen is diatomic. That's why it's N2. Okay, it's one of our diatomic gases. So we have to balance this. So I've got one sodium and one sodium. I'm okay. Nitrogen, I've got 3 of them, and over here I've got 2. Ooh, 3s and 2s. What do 3s and 2s both go into? That's right. I have to look at my least common multiple again. So what is my least common multiple between 3s and 2s? Hopefully you said 6. So how many 3s do I need to get 6 nitrogens? I need 2 of them. And how many 2s do I need to get 6 nitrogens? I need 3 of them, right? So that balances our nitrogens, but notice this 2 here also multiplies my sodium. So I need to go back and I need to multiply my sodium to make it fit, okay? Let's look at ammonium nitrate breaking down into dinitrogen oxide and water. So I've got one nitrogen there and one nitrogen there. I've got 2 here. So far I'm okay. Here I've got 4 hydrogens. Here I've got 2. What can I multiply 2 by to get 4? Did you say 2? Okay, and then I've got 3 oxygens here. I've got 1 oxygen here, and 2 times 1 gives me 3. So there we go. All right, aluminum oxide. What's the charge of aluminum? Did you say +3? And oxygen, -2, decomposes into its elements when electricity passes through it. So how am I going to put a 3 and a 2 together? That's right, 2 aluminums and 3 oxygens will add up to a total charge of 0. And it's going to break down to its elements. Why did I put O2? Do you remember? That's right, oxygen is diatomic. And because it's diatomic, it comes in groups of 2. So here we go. Let's balance this. Notice once again, I am writing a skeleton equation with the correct formulas first before I go and balanced. Okay, so I've got 2 aluminums here. Let's put in 2 here. I've got 3 oxygens here. I've got 2 here. Ooh, groups of 2 and 3 again. I need to find my least common multiple, which again is 6. So how do I get 6 oxygens? I need to multiply this whole thing by 2. How do I get 6 oxygens here? I need to multiply my whole thing by 3. Notice this 2 is also multiplying my 2 aluminums here. So I don't need 2 aluminums. I need 4. Okay? Nickel 2. So that means the nickel is charged +2. Hydroxide. Hydroxide is one of our polyatomics. So let's look at our polyatomic sheet really quick. So if I look at my polyatomic sheet, hydroxide is OH, -1. So OH, -1. What ratio do I need between those 2 things to make them zero out in terms of charges? 1 nickel 2 hydroxides. And it decomposes to produce nickel 2 oxide. So nickel still has its charge of +2. Oxygen has a charge of -2. What ratio am I going to need to do there? 1 and 1, right? Nickel and 1 oxide and water. Okay, so now let's go back and balance this. So 1 nickel, 1 nickel. 2 oxygens here, 2 oxygens here. 2 hydrogens, 2 hydrogens. So we're balanced. Okay? So here we go. That is decomposition. We're taking a complex molecule and we're simplifying it. Okay, single replacement is a reaction where one of the atoms of one element replace the atoms of another element in a compound. This is called a single replacement reaction. I like to call it the Mean Girls reaction. Okay, if you've ever seen the movie Mean Girls, you'll kind of know what I'm talking about. At the beginning of the movie, Katie Stanton is off by herself, right? She comes in, and by the end of the movie, she has replaced Regina George as queen of the high school. So one element replaces another element in a single replacement reaction, okay? So metals will replace hydrogen or another metal. I like to say positives replace positives, and nonmetals will replace other nonmetals. Negatives will replace negatives. Okay? So positives replace positives, negatives replace negatives. Okay? So here's our generic equation right here. We have A that's off by its little lonesome, and then we have BX that's together. And then in the end, we have AX together, and then B is off by itself. So notice that A here just takes the place of B. Okay? So here are a few examples. We have copper reacting with silver nitrate, and in the end we get silver and copper nitrate. Okay? So notice that copper is off by itself right here, but over here it's with the nitrate. And silver on this side is with the nitrate, and here it's off by itself. So silver and copper really just switch places. Okay, so let's look at how we are going to balance this equation. So I got 1 copper, 1 copper. I'm okay with that. I've got 1 silver and 1 silver. I'm okay with that. Notice I've got this nitrate group and it stays together. So I'm going to balance it as a group. I've got 1 nitrate group and I've got 2 of them over here. So that means I need to go and double my nitrates over here, which means I've doubled my silver, which means I also have to double my silver here. Okay? Now, I have fluorine gas and sodium bromide, and then I have sodium fluoride and bromine. Positives aren't always going to be the ones switching around. In this one, it's the negatives that are switching around. So this would be like a mean boys reaction, right? Remember, positives switch with positives and negatives switch with negatives switch with negatives. So fluorine here switches and becomes part of sodium fluoride, and then bromine gets left out on its own. Okay, so let's balance this. I've got 2 fluorines, and here I've only got 1 fluorine, so I need to double this. This gives me 2 sodiums, so I need to double this sodium bromide. That gives me 2 bromines, and there I have 2 bromines. Okay, we're going to leave these next 2 for next video. Okay, double replacement. So if single replacement is one element switching places with another element, what do you think double replacement would be? Yeah, all the elements switch. So we have 2 switches going on. Everyone switches partners. So if you've ever seen the Disney movie Enchanted, of that cartoon princess that comes up through the manhole in New York, that cartoon princess was played by Amy McAdams, and she meets this gentleman in New York, and by the end of the movie, Prince Charming comes chasing through her, trying to find her in New York, and by the end of the movie, Prince Charming ends up with Idina Menzel, who is the New York woman, and the princess, Amy McAdams, ends up with, I can't remember the name of the actor, but everyone switches partners by the end of the movie. So, A and X. Notice A by the end is with Y. And then B is with Y here, but by the end, B is with X. So everyone switches partners in a double replacement. By the way, some people call double replacement double displacement. Oh, and let me also, up here, single replacement. Sometimes single replacement is also called single displacement. So if you read it in a different chemistry book, sometimes they're going to call it single displacement or double displacement. Old chemistry textbooks called this metathesis. Okay, not many chemistry textbooks call it metathesis anymore, but old chemistry textbooks do. Okay, so here's another way of looking at it. Everyone switches partners. So let's do a few examples. So we have sodium hydroxide reacting with copper 2 chloride, and in the end, sodium gets together with the chloride, and copper gets together with the hydroxide. Do you see how everyone's switching partners here? So let's balance this equation. So 1 sodium, 1 sodium. I'm okay so far. Notice our hydroxides travel in a group, so I'm going to balance them as a group. I've got 1 hydroxide here. I've got 2 here. So I'm going to double this, which means I need to go back and double my sodiums right here. Okay? I've got 1 copper, 1 copper. I've got 2 chlorines and 2 times chlorine right there. We're good. Okay? And this next one, let's see, I've got potassium cyanide reacting with hydrobromic acid. Then I get potassium bromide, and I get cyanic hydrogen cyanide. Okay? So potassium switches places to be with bromine, and hydrogen switches places to be with cyanide. Okay? So let's balance this. 1 potassium, 1 potassium. I'm okay. 1 cyanide group. Notice it's a group, and 1 cyanide group. I'm good there. 1 hydrogen here, 1 hydrogen here, 1 bromine here, and 1 bromine here. Sometimes things are just balanced the way they are. Okay? We are going to do this next one next time. Combustion. Combustion, in a combustion reaction, oxygen combines with a substance that is made up of carbon, hydrogen, and sometimes oxygen, and releases energy in the form of heat and light. Oxygen can combine in this way with many, many different substances, making combustion reactions very common. We will focus on combustion reactions that involve hydrocarbons and carbohydrates. The products of these combustion reactions are always the same. It's always carbon dioxide and water. So we always will have carbon, hydrogen, and sometimes oxygen. Not always oxygen. I'm going to erase that. With oxygen, and it's always going to give us carbon dioxide and water. Always, always, always. Okay? So let's make that a Z. Here are some examples. So this is what's happening in our furnace at our homes right now, keeping our homes warm. We have methane, which is mostly what natural gas is made up of. Oxygen, giving us carbon dioxide and water. So when we balance these, I always want you to do carbons first. Always do your carbons first. Do your hydrogens second, and do your oxygens last. Okay? So we're going to do our carbons first. I've got one carbon. I've got 4 hydrogens. Here I've got 2. So 2 times 2 is 4. Now I'm going to look at my oxygens over here. I've got 2 here plus 2 more, so a total of 4. So what do I need to multiply 2 by to get 4? Hopefully you said 2. Okay, let's do one more. Liquid octane. So this is what is the primarily big ingredient in our gasoline. Octane is mostly what gasoline is made up of. We're going to burn this in the presence of oxygen. It will give us carbon dioxide, and it will give us water. Okay? So always write that skeleton equation first, then go back and balance it. Okay, we're going to do our carbons first. I've got 8. So that means I need to multiply my carbon dioxide by 8. I've got 18 hydrogens. So how do groups of 2? That gives me 9 waters, right? I'm going to look at my oxygens over here. So 8 times 2 is 16. 9 times 1 is 9. 16 plus 9 gives me 25. Can I do 25 with groups of 2? No, I can't. So what I have to do is I'm going to have to go back and double everything. So if I double this, double this, double this, this now gives me 50, right? That will be 32. 16 times 2 is 32, and 18 times 1 is 18. So that gives me 50 oxygens. What's 50 divided by 2? 25. Okay? So that is combustion. All right? We want to go back to the first examples in this chapter and classify the reactions that we balanced right like the very first day as to the types. So let's go back and look at these that we balanced way at the very beginning. Do you remember these that we did a couple days ago? Okay, so we're going to look at reaction types here. Going to get yet another color of pen. Okay, let's look at example 1. I've got copper and oxygen getting together to make copper oxide. I'm taking 2 simple things and I'm putting them together to make something more complex. So isn't this synthesis? Okay. All right, number 2. I've got potassium and water, and then I give potassium hydroxide and hydrogen. Look at that. I want you to think of water as HOH. Doesn't this hydrogen switch places with the potassium? Yeah, this is a single displacement. Single replacement or single displacement. Okay, so I want you to go through the rest of these and see if you can see the patterns here, and come back and check in a minute. You ready to check? Okay, calcium is with chlorine here, but calcium's with sulfate over here. Sodium's with sulfate. So isn't calcium just switching? Aren't they all just switching? Sodium's with chlorine. Yep, this is a double displacement or a double replacement. What about this one? We've got ammonium and dichromate, and then we get chromium 3 oxide and nitrogen and water. This is one complex thing breaking down into simpler things. This is decomposition. Okay, so here I have carbon dioxide and water getting together to make sugar and oxygen. This is synthesis. This is photosynthesis. Okay, and tin and sodium hydroxide, and then I get sodium tin oxide and hydrogen. I've got some relatively simple things, and I'm creating a more complex thing. And yes, I have this hydrogen off to the side. This is mostly synthesis. Okay, this next one, I've got carbon, hydrogen, oxygen, then I have carbon dioxide and water. Anything that has carbon dioxide and water as products, your brain should go, this is combustion. I'm taking a carbon, hydrogen, and I'm burning it. Okay? Aluminum and sulfuric acid, I get aluminum sulfate and hydrogen. Notice that the aluminum and the hydrogen are just switching places. So this is a single replacement or displacement. Okay? Iron and fluorine are getting together to make iron fluoride. That is a synthesis. Okay? So, synthesis, if it will let me write. So iron and iron fluoride synthesis. Synthesis on that one. All right? And then, let's see, sulfur trioxide and water getting together to make sulfuric acid, that is also a synthesis. Okay? And then this last one, sodium and magnesium iodide, and then sodium gets together with the iodide and magnesium is off by itself. This is a single replacement. Okay, and then I think, yep, that is, and this last one is synthesis. We have vanadium getting together with oxygen and making vanadium oxide. All right, so that also is a synthesis reaction. Okay, so hopefully you know your reaction types and you're getting more comfortable balancing. We'll see you later. We'll talk about actually predicting reaction products next time. Bye.